Welcome to the next video. In this video we will discuss the Ampere's law of magnetism. Uh, we had studied that electric field and magnetic field are one and the same, are the two sides of the same coin. So in electric field, like we have Coulomb's law, which gives a general definition of how to find force and electric field due to an electric charges. And in electric field we have Gauss law. And in Gauss law, this helps. Coulomb's law and Gauss law tells us the same thing but in a different way, and Gauss law helps us to use the power of symmetry to simplify finding solutions to some of the complicated problems in a easier manner by using the power of symmetry. Similarly, in magnetic field, because electric field and magnetic field are same, it only depends on the reference frame which you are in, as we had discussed some videos back. And so, like Coulomb's law, we have in magnetism Biot-Savart's law, which gives us a general way of finding a magnetic field due to current or charges in motion. And like Gauss law in electric field, we have Ampere's law in magnetic field. Okay, so the statement of Gauss law is the flux of electric field through a closed surface. So we had studied that closed is an important term in Gauss law, closed surface. So the flux of electric field in a closed surface is equal to charge enclosed. So charge enclosed is an important term, enclosed inside the surface, inside the closed surface, divided by epsilon naught. Okay, so this was the statement of Gauss law. So because the corresponding statement for magnetism in Ampere's law is the circulation, and here, like here, the flux was surface integral of E ds. Okay, here the circulation is defined by integration of B ds. Okay, in the circulation, so the statement goes like this, that circulation integral B dl of the resultant magnetic field along a closed plane curve. Okay, so here also the important thing is it like Gauss law, it's also defined by a closed, but the difference is it is a closed plane curve. Okay, so in Gauss law, the flux was through a surface. Okay, so here let me write this, the flux through a closed surface was the statement of Gauss law. The slight difference in Ampere's law is, with respect to magnetic field, is circulation. It's now here it's not a flux but a circulation. We'll just quickly understand what is meant by circulation. Mathematically it is B ds, integral of B dot ds. Sorry, here because it is a closed curve, it will be B dl, not ds. Okay, so the difference is, here it is E ds, or surface integral over the surface area. Here it is integral of B dl, or closed plane curve. So here length is the unit, here area was the unit in Gauss law. So the circulation integral of B dl across a plane, closed plane curve, so closed is important, is equal to mu naught times the total current crossing the area bounded by the closed curve. Okay, so here is an example. Okay, so it will be more clear if we discuss the example. Here what the mathematically it is saying, for integral of B dl is equal to mu naught times I, and here it was q naught times 1 by epsilon naught. Okay, so Ampere's law is the same as the Gauss law with some slight difference. Here the magnetic field is integrated over a closed plane curve. In Gauss law it was integrated through a surface. Now it is integrated through a across a plane curve. For example, I have taken here a circle. Okay, and this term integral B dl, which is also called the circulation of magnetic field. Okay, because we go round in a loop inside a closed, we circle around a closed loop. That's why it is called a circulation. Here it was called flux because it was integrated over an area. Here it is defined as a circulation because it is integrated over a curve. So this is equal to, here it was charge, okay, stationary charge. We know that magnetism, electricity is related to stationary charges. So here it is Q naught. So obviously if we just we can anticipate it because magnetism is related to motion of charge, and motion of charge is nothing but current. This term must be current or motion of charge in place of Q in the Gauss law. So here it is I. So it is dependent on I, which is inside, closed inside the loop which we are considering, mu naught I, and it, the constant here, it was 1 by epsilon naught. Here the constant is the magnetic constant of mu naught. So this is the statement of the Biot-Savart's law. And just to give you a further explanation, if I have any closed loop or closed curve, not here, it in this case closed curve, and suppose suppose I have some current here. The current is flowing inside this into the screen of paper, some current flowing out of the screen of paper. I have a wire in which current is flowing out of the screen of paper, and I have currents all along the outside here. Okay, and if I take the magnetic field B here, okay, and I integrate, I use the term B dl. Left hand side is nothing but if I take a small element in the curve dl and multiply B dl and add all the small B dls across the full curve. So I use the integration sign to add all the term B dl terms. So this will be one B dl, here one B dl will be there. So all the small addition of all small B dl is the integration of B dl in the left hand side. Right hand side tells us is that I need, for suppose this is I1, this is I2, this is I3, this is I4, I5, I6. So I need to consider, like the Gauss law, only the currents which are inside this closed loop. Okay, similar to Gauss law where we considered the charges inside the closed surface, here we have to consider only those currents which are flowing inside this closed loop. So the currents which are flowing inside the closed loop is, so this will be, right hand side will be mu naught times, so I1 is flowing inside, so I will write it as minus I1. I2 is flowing outside or coming out of the screen, so I will let me take the convention of the current flowing outside the screen is positive and inside the screen is negative. So here this is negative as per our convention, minus I1 plus I2 minus I3. Okay, so now this can be used. So let us solve one simple problem which we have already solved using the Biot-Savart's law, and again we will see that how using the Ampere's law and the power of symmetry we can simplify these problems. Okay, these type of problems. So let me delete this so that I have some space. Okay, so my Ampere's law says, Ampere's law says that circulation of magnetic field, which is the curve integral of B dl along the length, is equal to mu naught by I. So if you remember, we had derived in our last video that how if a current carrying wire is making an we can find the magnetic field I at a distance d due to a current carrying wire. And if you remember, we had used lot of mathematics, used integration, took a small element here dl, and used Biot-Savart law, mu naught by 4 pi I dl by r squared. Okay, and then I integrated this to find what is the relation, what is the magnetic field, and I had defined from angle theta 1 and theta 2, and it was very complicated. It was theta 1 and theta 2, and once I found the relation of magnetic field in terms of theta 1 and theta 2, then to find the what is the magnetic field due to a very long wire, I approximated theta 2 to 180 degree and theta 1 to 0 degree. And after doing all those stuff, if you go back to that video, you can probably recall, but after doing all those stuff and after about 15-20 minutes of derivation, we had concluded that due to a very long wire, the magnetic field is B is equal to mu naught I by 2 pi d. Okay, so that can be done using the basic Biot-Savart's law. But why we need another theorem? Because this Ampere's law makes our life easier in case if there is a symmetry. So suppose this is a very long wire, okay, which is coming out of your screen and going inside the screen. Very long wire. I have taken the top view of that wire. Okay, and because I have taken the top view of the wire, let me define a direction of the current. So suppose the current either can flow inside the screen or outside the screen. So let me assume that the current is flowing outside the screen of your computer. So for that notation, if you remember the sign convention or the notation convention, I can put the current as this and with a dot in it to imply that the current in this wire is flowing out of your screen. Now if I draw a circle of radius d around this, okay, so this is the circle of radius d. All these points are symmetrical with respect to the center. Okay, this is also at a distance d, this is also at a distance d, because it is a circle with the center at this point. So this is a symmetrical situation, and we know from symmetric situation, because it is symmetric, it is equidistant from this wire, the magnetic field due to this wire should be same at this point, should be same at this point, should be same at all the points on the circle, because all the points are symmetrical with respect to this. Okay, and we know if we use the right hand thumb rule, which we had discussed in last class, that the direction of current will be, because it is coming out, okay, if I use the direction, if I use my right hand thumb rule, my magnetic field will be along this direction, anti-clockwise direction. Okay, so at this point the magnetic field will be going tangentially like this, at this point the magnetic field will be going tangentially like this, at this point magnetic field will be going tangentially like this. Okay, so dl, let me take a very small element dl here. Okay, dl. So what is the direction of dl? Direction of dl is also along the direction of the current. Okay, so here also dl is, the direction of dl is this. Okay, so dl and b are making a 0 degree angle with each other. Here also, like, let me take a small angle dl, and dl will make along the direction of the along the anti-clockwise direction. So dl is this. So dl, if I draw a tangent, dl will make a 0 degree angle with b, and we know that b dot dl is nothing but b dl cos theta. So my left hand side will become b dl integration of b dl cos theta, and cos theta is 0, so I can cos theta is 1, so this term becomes 1. Okay, so this can be replaced by 1. So integration of b dl will be equal to mu naught times I. So now here only one wire is there, and that is flowing out. So according to my convention, that is a positive value, so plus I. Okay, so this, because b is constant, let me evaluate this. B will come out of integral sign. B dl will be equal to mu naught I. Okay, and we know that integration of dl is nothing but addition of all the small lengths of the wire. Okay, So if I do integration of bdl, evaluate integration of dl, it is nothing but the total length of this circle, which is 2 pi r, or the circumference, or 2 pi d. I have taken d as the radius, so 2 pi d is equal to mu naught I. So this becomes b is equal to mu naught I by 2 pi d. 2 pi d. So we see here that such a complicated issue, such a complicated formula means earlier I had to do so many integration and approximation and limits to find this value. All those complicated things has been just reduced to these 2 steps. Okay, and we can easily find, with the power of symmetry, we could use the Ampere's law to find the magnetic field in just 2 small and very easy steps without requiring much mathematics. So this is the power of Ampere's law, and we will again use the power of this Ampere's law to solve or to find out the magnetic field because of some more complicated formula. This was an easier problem. So let us use the Ampere's law to find the magnetic field inside a very relatively more complicated scenario. So first let us discuss solenoids. Okay, so we had discussed that if I have a circular current carrying wire in last class, let me take the direction as anti-clockwise direction, and then because of this circular wire there is a magnetic field at the center, and we had derived that because of the circular carrying wire the magnetic field at center, if you remember from last lecture, mu naught I by 2a or 2d, where this a or d is the radius of this. So we know that one loop of wire will produce a magnetic field inside. What if I have many loops of wire, circular wire, and this is like a spring and this is called a solenoid? So I can have a direction of, suppose let me say that the direction of current is like this here. Okay, so current is flowing like this round, and here it is going like this, round and round. Okay, so if you look, if I take a cross section, okay, if I just take a cross section and look, I cut this, suppose this is x plane. Okay, suppose this is x plane, this is y plane. Okay, and the plane which is coming out towards your screen, out of your screen, is the z plane. Okay, so if I just take that xy, a section of this solenoid across the xy plane, I cut it along the xy plane, I will get something like this. So this is the, I could write, this is the x direction and this is the y direction. So I have cut it, and you see that bottom the current is flowing in, and again towards the top it is coming out. Again it is going round in a circle. In the bottom it is going inside and current flowing like this, and again at the top it is coming out. Again at the bottom it is going in, and the top it is coming out. Okay, so that's the current. These are the wire, cross section of that wire, and here the current is coming out, and after going through the full circle, or half circle, it is going in. Again after coming to half circle it is coming out, and then again after completing half circle of travel it is going in. Okay, and at the center, okay, the magnetic field will be pretty uniform, can be assumed to be uniform, and it is shown like this. Okay, so let me use Ampere's law to find out what will be the magnetic field at a point inside this solenoid. Okay, so let me take a small closed surface, okay, in the form of a rectangle here, because we have to use BDL is equal to mu naught I. Okay, so BDL will be taken as mu naught I. So I have to do integration of mu B across a closed surface. I need to define a closed surface. So I am defining now the closed surface as a rectangle here. So let me say that the length of this rectangle is L, breadth is B. Okay, so here let me start from this point. Okay, let me start from this point. Okay, so length, suppose this is length 1, this is length 2, this is length 3, this is length 4. Okay, now I have to go across all the surface, add do integration of BDL through surface 1, 2, 3 and 4, and then find out, use Ampere's law to find out B. Okay, so integration of BDL will be integration this is integration sign should be there, integration through length 1 plus integration through length 2 plus integration through length 3 plus integration through length 4. So length 1 plus length 2 plus length 3 plus length 4. Okay, so let us study. Here outside this solenoid the magnetic field can be assumed to be 0. So B for the BDL for outside can be taken as almost equal to 0. Here it is assumed that the magnetic field is very weak outside this solenoid and it can be neglected. So I am neglecting this term. Now let us consider across length 2. So across length 2 the magnetic field is like this and length is like this. Okay, length, so magnetic field is going out in a perpendicular manner to this length, and we know that B dot dl means B dl cos theta, and cos of 90 is 0. Okay, so because the magnetic field is flowing perpendicularly out of this second surface, and perpendicular means cos of 90 is 90 degree and cos of 90 degree is 0. That means this second term will also come to be 0. This is already neglected, 0. Let us evaluate the third term. Third term, the length is like this and the magnetic field is also along the length. Okay, so here it is making a cos of 0 degree. So integration of BDL will be BDL. So cos 0, which is 1, and integration of dl along this is just the total length of this side, which is L. So this can be written as BL. Okay, so I have one term here. The third term evaluates to BL, and fourth term also, fourth side, like the second side, magnetic field is going perpendicularly inside, and so I can because the magnetic field is perpendicular, this fourth term is also 0, like it was 0 in the second term. So the left hand side just becomes now total is BL. So left hand side gets evaluated to BL. Let us see what is happening to the right hand term. Okay, so let me say that the solenoid has a lot of turns. Okay, so let me define the number of turns per unit length is equal to n. Okay, let me define small n as the number of turns per unit length. Okay, number of turns per unit length is small n. Okay, so what will be the total number of turns inside this box if the number of turns is per unit length is n? So the total number of turns inside this box, or total number of circles inside this box, will be just n times L. Okay, so the total number of circles inside this box is the number of turns per unit length multiplied by the total length of this box. And so if there are NL circles here, what is the total current inside this box? Total current inside the box is the total number of the wires or the circles here multiplied by the current in each wire. And if I flows here, so same I will flow through all the circular loops, and so the total current in all the circular loops is just the total number of loops, which is NL into I. Okay, so this I will be, the total current inside this box will be equal to NL into I. So the right hand side now becomes mu naught times NLI. So if I just do BL, left hand side was BL, is equal to mu naught times NLI. So length Now the length term gets cancelled on both sides, and it simply becomes B is equal to mu naught Ni. Okay. So we have used the Ampere's law to solve, to derive what is the magnetic field inside a solenoid. Okay. And one important point to remember is here B is equal to mu naught Ni, and here small n defines the number of turns per unit length of a solenoid. Similarly, one final discussion. Let us again derive what is the magnetic field inside a toroid. Okay, what is the magnetic field inside a toroid? Solenoid was just circular turns in a linear way. Okay, toroid is the same wires are wound in a circular magnetic material. So again, let us use this Ampere's law to derive the magnetic field inside a toroid in this complicated case. So again, the Ampere's law is mu naught integral of B dl is equal to mu naught I. So first I have to define one area or one linear surface, as we saw that not surface but a closed curve. I have to define a magnet. The Ampere's law is used for a closed curve. So let me define a closed curve which say passes inside this toroid. Okay, a circle which is going inside or in the through the middle of this toroid. Okay, so let us assume, because for symmetry again, each and every point inside this center of this toroid is symmetrical and there is no difference. So I can assume that the magnetic field, because of symmetry inside each and every point inside the center of this toroid, is same, and let me say it as B. Okay, so again here the left hand side will become integration, B will come out, integration dl. Let me say that the radius, the central radius of this toroid is r. Okay, that will be required. Here in this figure it is written x. Let me tell it as r. Okay, so this is equal to mu naught I. Okay, so let me say define that the total number of turns. See, the definition of here I am defining as a total number of turns. Okay, capital N. This you please keep in mind. How we define solenoid? Small n was the number of turns per unit length. So in this formula for solenoid, n is the number of turns per unit length. Okay, but in toroid the formula which I am deriving is in terms of capital N, which is again the total number of turns. Okay, we'll see that both formulas will come to, if we'll discuss it once we derive it. I don't want you to confuse you now, but here n is the total number of turns. So if n is the total number of turns, then mu naught I, so total current flowing inside this loop is total number of turns multiplied by the current through each turn. Okay, so the total mu naught, total current inside this is equal to total number of turns multiplied by the current flowing across each turn. And here again integration of B dl. So integration of dl is the total circumference of this wire, which is B into 2 pi r is equal to mu naught Ni. So taking this term to the right hand side, B is equal to mu naught capital Ni by 2 pi r. So this is the formula which is generally used in textbooks. Okay, if you compare this with our solenoid equation was just mu naught small ni, where small n is the number of turns per unit length. Okay, and in toroid it is mu naught capital Ni by 2 pi r. Okay, but where n is the total number of turns, But if you want to write in terms of small n, which is number of turns per unit length, so n by, so total length is of this toroid is 2 pi r. So n by 2 pi r is nothing but small n, or the number of turns per unit length. So if you finally compare that equation, the final formula in terms of small n is same for both solenoid and toroid, but it's generally, which is mu naught small ni, both for solenoid and toroid both are same. But in terms of capital N, because we generally deal for lengths, we generally deal with small n, and with for circle, because we know what is the total number of turns, we generally deal with capital N. So this is the formula which is finally used in most of your physics textbook. So good news is that with this we have completed a discussion on the magnetic field. In next videos we will discuss something related to permanent magnets and magnetic field of earth and all those stuff, and I will try to quickly cover those because I find them not to be that interesting, but still if other people might be interested in those. Also magnetic properties of matter, what gives gives materials magnetic properties. We will quickly go over those topics in next few videos. So see you in next video.